So we're going to switch gears a little bit and go into nutrient deficiencies. So if I look at the plant, how can I visibly see, or the plant is talking to me, what it has a deficiency in? So this is off the internet, but it works the same way for all leaves. So this is a thing showing a corn leaf, but it wouldn't matter whether it was corn or any other plant. So we're going to look at nutrient deficiency problems. We're going to look at the colorations, cupping, any of these, and they'll be able to tie to deficiencies. One thing we do need to understand is sometimes maybe it shows a deficiency, but you actually have a root problem, maybe a fungal relationship or bacteria. So if you keep putting in the best compost, everything's good, maybe there's something wrong with maybe the roots. So you can get down and see if there's something wrong. So you have to have healthy roots for this to work. But assume that your plants are healthy, then you can look at deficiencies. So the concept we want to go over is observe for yourself. You go in your garden, you can make the observations. There's only 4, so it's not that difficult. A healthy corn plant or any leaf is deep green and glossy. So let's just say a stereotypical, doesn't look like anything's wrong with it. Really nice, healthy leaf. A leaf from a plant with a nitrogen deficiency is going to have a yellowing midvein. So if we start to see yellow down its midvein, yeah, that would be an indication it's having a nitrogen deficiency problem, okay? So if I look at this one, I go, oh, well, I don't see yellowing on the midvein. So we'll see what's happening, okay? If it starts to twist and or have purpling, so purpling on the edge, that's a phosphorus deficiency, okay? So there's something wrong with the phosphorus. And if the leaf has the leaf is potassium derived, it has the yellowing on the outer edges, okay? So these are the 3 big minerals they call the 3 big 3. And then we're going to see later, they're tied to the other minerals. There's relationships to these and the other mineral sets. So this is basically what we do. Hey, is that going good? That's the big ones. Then we can investigate in different ways, smaller ones. So we'll see that. So what's happening here? Phosphorus deficiency, yes. So we've got purpling on the outer edges related to phosphorus. And here, nitrogen deficiency. So we have a yellowing of the midvein. And a potassium, so yellowing on the outer. It is funny, a lot of classes I ask that, and sometimes I don't say anything, like a minute, nobody says anything. It's like, read. Okay. Good teacher always tells you the answer to the question before. Have you ever noticed that? Yeah. Potassium deprived, yellowing on the outer edges. So these are just random things you can go in your garden, and if you start to see this, you see the plant, some of them, the leaf is not having a problem, but this one is. It's indicating there's probably a potassium problem. And this particular plant, sunburned. Oh, wow. So that birds of paradise, and when we find those naturally, they're typically not in full sun. So in this instance, if it's right, we put them outside there, and it's getting that full sun, it actually can get sunburned. So how people not grasping that? It's probably not, and that's probably also an indication it doesn't have enough water. So it's sitting in the full sun, trying to cool itself, but it can't. It doesn't have enough water. So then it is wilting and it can get sunburned. And then here, this is a plant that's been put inside of a box. It has oxygen deficiency. So sometimes house plants actually have issues with an oxygen deficiency. All day long, they're locked in the room. You come home and what's going on? What we'll notice here is the stem is still strong. So it doesn't have a water problem. It's got good stem, but the leaves are down. That would be oxygen. So here, the stem is down. It has water deficiency, so it's not getting enough water. So we want to look at how we can avoid soil deficiencies. So we can see the plant telling me I'm having a problem, but the best thing to do is avoid a plant having a problem. So this is basically how the soils are absorbing minerals. So you have on the root with the epidermis, and there's what they describe as a root hair. It's like microscopic. You can't really see it as such. And it goes between like basically injects itself almost into the minerals, which were the quartz grains. In between them, we had the polysaccharides with the bacterial colony, right? So you can almost identify like it injects it's into there. And so that's the relationship. And then we're going to see that the minerals are carrying positive charges, and the plant is a negative charge. And then switches with an ion. So this is called the cation-ion exchange. Negatively charged soil particles or minerals being exchanged through an electrical charge. That's why the pH test, when I have pH is potential hydrogen. So they actually stick a probe, which is just 2 pieces of copper to the ground. And the electrical charge that's measured is the potential hydrogen, which says how much potential there is to exchange minerals. And then we'll see later that different minerals are at different electrical levels, thus pH, acidic or alkaline. So we'll go through the plant nutrients and what each nutrient does. So if I see this deficiency or if I add more of this nutrient, what happens? The big 3 in purple there, nitrogen, potassium, and phosphorus, NPK. So nitrogen, vegetative growth, the size, how big does the plant get or how big is the tomato? Pretty much tied to nitrogen. Phosphorus is root growth, so the health of the roots. And remember, healthy roots can also derive, if they're unhealthy roots because you have a phosphorus deficiency, you may have other deficiencies because you can't actually get the minerals. The fruit, the size, like if it actually fruits. So that could be like flower sets and fruits. Photosynthesis, and if you're not getting good photosynthesis, then the plant can't exchange sugars well, then it doesn't get the minerals either. So these things become tied together. Potassium is disease or pest resistancy. So if you're seeing your plant having a problem with fungal diseases or anything like this, or bugs are getting it, may have a potassium deficiency. So now the secondary ones, magnesium is production of chlorophyll, photosynthesis, and the movement of phosphorus. So if I have a magnesium deficiency, I can't move phosphorus, so I may have photosynthesis, root, or fruiting issues because of the magnesium deficiency, which creates the deficiency to have the other one. Calcium is the growth of the cells, so meristem growth, or the cells, building the cells, also very key for flowering plants. Sulfur is chlorophyll production and flavor. So when people were only back in the 1950s, 60s, even up into the 70s, they were really only putting NPK onto vegetables, and people were complaining in the market, well, this vegetable doesn't taste good. Well, our chemical boys got smarter and started to add, so now they add a cocktail of stuff, and one of them being high sulfur levels, and that's why you don't see the organic taste test anymore, because you don't want to take that non-organic tomato with an organic tomato, guys, and you don't want to put a blindfold on and have them videotape you. You wouldn't want to play that test. If we would want to see that on YouTube, this is the issue. They're jacking up, just like kind of like MSG, right? It jacks the flavors up. So they're putting in more, so you get a more intense and what we say flavorful, but that doesn't mean better. So what we can also do is recognize that if we recognize how to, and we'll see later charts, how do I get extra sulfur into my garden? And if I have a higher sulfur level, because I know the affiliation of my foods with flavor, guess what my food will do? Taste better than someone who doesn't have a high sulfur level. So that's why it's important to test and know how to get sulfur, for instance. Iron is chlorophyll production, magnesium chlorophyll. Boron is the availability of calcium. So if I have a boron deficiency, then I can have a calcium deficiency, and the calcium deficiency can pull up again to one of the big boys. Zinc is enzyme functions and or pollen, so it won't pollinate, so it doesn't germinate correctly. Molybdenum is nitrogen uptake. So if I have a molybdenum deficiency, right, I can't take up the nitrogen even if it's present. So my plant might not be growing well, and my test says I have a lot of nitrogen. I keep putting in lots of greens into my compost. What's the problem? Maybe you have a minor nutrient deficiency, okay? So other things that control that, so we need those things to be present, but we also have to have water retention capacity in our soils so that the bacteria will have a place to live. So if they're not there, they can't exchange. So this is called hygroscopic, capillary, or gravitational water exchange. What we're looking for is when we have water available at the root. So the root can only take it in if the water's there. The water drains out, it can't take the water up. So it needs constant water. So it's a pump. It's pumping water up and out constantly. Okay? And we go sit it in the sun, in full sun, getting baked, and we're not watering, it'll get sunburned. That's an affiliation. If you have really, really high suns, like in the tropics, that's why we'll see a lot of times that the Thai gardeners actually putting up what they call slam, which is a filter fabric. And they have filter fabrics they'll put up and filter out 80%. Okay, and then in garden, what we would think as vegetables under filter fabric as high as 80% blockage. Then that's how strong the sun is. So this is things that we will look at. When we look at the permaponics in the morning practical, permaponics is designed to make sure that the capillary action is always held. So it can never get above or below because the drain is set exactly at the wicking point for capillary action. Capillary action is basically, if I take my shirt and I put a pan on this table and I dip my shirt in, and it just barely touches the water, it will soak the water up, right? Contrary to gravity. That's capillary action. It's actually friction that pulls the water up to the point that it doesn't go any higher. That's the wicking point, and then our plant roots will come and just touch that. And right when they're in there, they say, wow, this is nice, I like it. And they can continue, and especially prevalent if you're doing anything like leafy lettuces and things. If your lettuce doesn't have water for like up even 3 hours, it'll go bitter. And then it doesn't go back. So if you want really fresh, crisp, perfect, sweet, if you will, sweet lettuce, that's why the permaponics, when we were running the lettuce systems, it was like, wow. People were like, how did you get it to do that? It 24 hours a day has perfect water, okay? Besides the fact that it's in compost, not in say, chemicalized agriculture. So this is crucial for your soil health. So we have what's described as saturation, meaning it's so much water it's draining through. At this point, you could leach your nutrients. Okay. Field capacity means it's perfect, and or that capillary action. And wilting, if the plant, there's no access, the water has drained through, and it's sitting there going, I don't know what to do. So think about water retention is also tied to what the material is made out of. So humic materials, remember the relationship that the worm castings could hold 10 times more water retention capacity than humic material, right? So that 20% of worm castings is also 10 times more water retention than, say, the compost. And then we put in the compost plus the char. So what we're working on is trying to create that designer capillary action. So then the plant that's in it has the access to water, and the water is where the nutrient exchange takes place because the bacteria lives in the water. So particles in the water, the cation-ion exchange, they have negative charges and they attract positive ions from the minerals. So the bacteria creating it, pulling it off, and then exchanging the mineral with the plant. Okay, so they have these three things. We need the mineral present, we need water for the bacteria to thrive, the bacteria exchanges with the plant, mycorrhizal hair sticks in because of the exchange of the glucose, which is the photosynthesis creating sugars. So that's how soil holds water, okay? So you also need to have air. Air pockets are essential. So if it's all water and there's no air, it'll go anaerobic or what's called sodic soils. If you have sodic soils and there's no air, you'll grow basically algae and things like this. And then what will happen is the algae will actually attach itself and colonize around the root of the plant, right? And then steal the minerals from the bacteria. So at this point, that's what's one of the more problems with hydroponics. If the hydroponics is running and it's in the sun, so it's heating up the water, and they don't aerate the water, so that's why they have air stones inside the hydroponic systems, in order to aerate the water to ward off it growing algae. If you didn't have the air, the algae will grow attached to the roots of your plants, and then they take all the food source from the water. So you highly aerated soils don't have algae. So aeration through soil organisms, we can do that with ants, worms, etc. They make what's described microcytes. These are always aerobic and anaerobic at the same time. So the anaerobic is inside the little droplet, if you will, where the bacteria is in the anaerobic condition, but it needs the aerobic for breathing oxygen, okay? And if you don't have oxygen, it'll be purely anaerobic, which will be sodic.